Okay, today I'm going to discuss about the topic which is called the diagonalization of a matrix. Or you can say diagonalizability of a linear transformation or linear operator. And to begin with, let me remind you a few things which I discussed in my last class. I told you that you have to keep in mind that if I consider two vector spaces over the same field, V and W, and if I define a mapping from V to W, which is of course linear, then such transformation or such mapping is called linear transformation. And the matrix representation of the linear transformation is constructed with respect to the two bases of the vector spaces V and W. So if we consider the basis of the vector space V to be beta and the basis of the vector space W to be gamma, I told you in the last class that the notation of matrix representation of the linear transformation T with respect to beta and gamma is denoted by this. We denote this by this notation. But if we consider the domain and the codomain to be same, we say that T is defined on the vector space V, or T is a mapping from V to V, which is linear, of course. And if the basis of the vector space is beta, then the matrix representation of such a linear mapping is denoted by T beta. Not only this, such a linear mapping is actually called linear operator. And you will see that most of the cases in quantum computing and machine learning, if you open the book, you will find that they emphasize on linear operators mainly. They choose a system, a physical system, which is following the rules of the vector space, and they define the mapping on it, and they always talk about the operator. Okay. So therefore, a new theory that has been developed later by the mathematicians, which is called the operator theory, which is a vast topic. I'm not going into the details of that. These are the first two prerequisites for my today's class. Also, I would like to remind you one definition that I discussed in my previous class. The definition was about, this is my second prerequisite, that I'm writing it in short. If beta is the ordered basis of the vector space V F, where dimension of V is n, that is the vector space is finite dimensional, then the standard representation of V, with respect to this basis beta is defined by the function phi beta of x, which is of course, you know, column vector. When we represent the vector x with respect to the basis element, we just consider the column matrix which contain the coefficient of the linear representation. And this is true for all x belongs to V. That I defined in my last class. And one extra information that we need for our today's discussion is the following, that I didn't define in my previous class. It goes like this. It is a new definition that I'm providing you, that let capital A be an M by N matrix, rectangular matrix with entries from field F. We define another mapping. We define another mapping which is denoted by LA, and it is from the vector space Fn to vector space Fm. You know, vector space Fn is the set of all n tuples, and vector space Fm is the set of all m tuples defined by LA of X is nothing but the product of the matrix and the vector X. This is actually called left multiplication transformation. It is actually called left multiplication transformation. And this holds for all X belongs to Fn. A very simple problem will make you understand what I'm talking about here. Say, for example, if I consider the matrix 1, 1, 0, 0, 2, 1, and you know this matrix belongs to the set of all 2 by 3 matrices, where the elements of the matrix have been chosen from the set of real numbers. Then if we define such a linear mapping from R3 to R2, where of course I have considered F to be R in the first case, and in the second case as well, where in the first case n is equal to 3, and in the second case m is equal to 2. And then for an arbitrary vector x, which I can take as 1, 3, minus 1, say for example, we will find by this particular definition that when LA acts on the vector x, it is nothing but the matrix multiplication with the vector from the left hand side. The vector is getting multiplied by the matrix from the left hand side. So actually we are getting 1, 1, 0, 0, 2, 1, and the vector 1, 3, minus 1. And you multiply this, you will get 1 into 1 plus 3, 1 into 3 plus 0, and that would be 0 plus 2 minus 1, and this becomes 4 and 1, which of course is a column matrix. You see, just look at this. The order of this matrix is 3 by 1, and the order of this matrix is 2 by 1. 2 by 1. So it belongs to R3 because I have chosen it from this domain, and the outcome belongs to R2. Okay, So this is the way by which this particular mapping operates. LAX equal to AX. Okay, so these are the few prerequisites that will be helpful for our discussion of the diagonalizability of the matrix. Now in the syllabus you will
Sir,
find,
won't it be, sir, excuse me, sir. In the
yes,
previous page, won't in the calculation part, won't it be 0 plus 6 minus 1? The
oh, yes, yes,
second
yes,
row.
yes. Sorry. It's my mistake. Sorry. It's my mistake. It would be, yeah, it would be 0 plus 6 minus 1. So that would be 5. Now, all right.
Yes, sir.
Yes, sir.
Okay. Now, what I was telling is that if you're in your syllabus, you will find that you'll find that they started with the concept of eigenvalues and eigenvectors. And later they have written diagonalization of the matrix. But the thing is not actually like this. Actually, eigenvector and eigenvalues are the parts of the study of the diagonalizability of the linear transformation. So that's why I will start by telling you why diagonalization of the matrix is so important and how out of this particular concept, the concept of eigenvalues and eigenvectors emerge. Why do we need the diagonal matrix is because if we have the diagonal matrix, it becomes easy for us to calculate with any diagonal matrices. If you want to take the product of the two matrices or product of any matrix by the vector from right or from left, diagonal matrix always makes the thing easier. So it would be better if we can find some diagonal representation of the linear transformation. If we can see that a linear transformation is available and its matrix representation is diagonal, then it is good for us. If it is not, that means off diagonal elements are present, then things become a little bit tedious. So the first question that arise in this type of study is the following. Question number 1 is there any ordered basis? Is there any ordered basis beta for V, the vector space V? Obviously, you always remember that my vector space is always finite dimensional, such that the matrix representation of the linear operator is a diagonal matrix. Diagonal matrix. So first of all, this is the question that we need to study in this particular topic, that is there any ordered basis beta? And if there is any ordered basis for a particular vector space, if such a basis exists, how can it be found? Okay. These are the two questions which will be discussed in today's class. So pay attention, and eigenvalues and eigenvectors are actually a very important topic. And of course, you can say that all the things that we studied so far were the prerequisites, which are actually the motivation for studying this particular topic, that is diagonalizability of the matrix. Diagonalizability of the matrix is a huge area, and many important results and methodologies are there, but we will briefly go through them, not all of them, those who are in our syllabus, and we'll try to understand the basic logic behind it. Most of the people, they claim that they understand diagonalizability. Most of the teachers, often I have seen that they somehow give the students a methodology of finding eigenvalues and eigenvectors. Symplectic approaches are there, but motivations are not discussed usually in the class. Okay. So remember, these are the 2 points, these are the 2 motivations for studying the diagonalizability of the matrix, and from them the concept of eigenvalues and the eigenvectors will emerge very beautifully. So my first definition is as follows, that a linear operator on a finite dimensional, let us name this linear operator as capital T, on a finite dimensional vector space V, on a finite dimensional vector space V is called diagonalizable if there is an ordered basis beta for V such that matrix representation of this linear transformation with respect to beta is a diagonal matrix. Remember that this definition is just a definition, it is not the working criteria. You know that every linear operator has a matrix representation, and every matrix representation can be associated to a linear operator. Okay. So for example, if I talk about the identity matrix, you know a 2 by 2 identity matrix looks like this. This is the identity matrix. Now you just look at this. This identity matrix is diagonal matrix. So it is of course diagonal. The corresponding matrix representation, since the matrix is diagonal matrix, corresponding linear transformation is obviously a diagonalizable. But we have never thought of the linear transformation that the identity matrix is associated with. We know that identity matrix, when multiplied by any matrix, gives you the matrix in return. Okay, so what we can do, if you think a little bit, we'll find that we can always define a linear operator from the vector space V to vector space V, where the linear, you can consider here in my case, the linear operator, the vector space to be M2 cross to R, such that for any vector, that is for any matrix belonging to M2 cross to R, when the transformation acts on it, the vector doesn't change. So TB equal to V is the transformation. And you see, if you try to find out the matrix representation of this, TB equal to V, then you will find that, of course, it will become same as 1001. Okay, so for example, how can I find this matrix representation? What is the basis beta for M2 cross to R? It contains these elements. These are the basis elements. And now you are going to act on this, the transformation. That is T of this matrix. This is my say V1, this is my V2, this is my V3, this is my V4. So T of V1 will give you 1, 0, 0, 0, which can be expressed as a linear combination of these basis elements. Again, So we can express this as 1 into 1 0 0 0 plus 0 into 0 1 0 0 plus 0 into 0 0 1 0 plus 0 into 0 0 0 1. Okay. And similarly, we can find other matrix elements. You will find other matrix elements like no, one thing I have the basis is wrong. Actually, I have written it incorrectly. This is not the basis for TV equal to V. I need to no, okay. No, just a minute. Since I have chosen any basis or any 2 by 2 matrix, so obviously this will remain. Sorry, this will be there. And with respect to the transformation, actually I am seeing that since my transformation is TV equal to V, so I will just look at how the basis elements changes with respect to this matrix, this particular transformation. And since on both the sides, that is on the domain side and on the codomain side, we have the basis beta and beta, and we know that once we express the basis, once we find the transformation on the basis element, then that particular outcome is again made to is again expressed with respect to the basis element of the codomain. But here codomain is of course beta, so therefore we will try to represent this particular element 1001 in terms of these basis elements only. And in this manner, if you try to find out the matrix representation, you will find definitely you are going to find a diagonal matrix with respect to this transformation TV equal to V. So the identity matrix is always diagonalizable. But suppose if I give you a matrix like this, 1 1 0 1, the question is, or if I give a matrix like this, 0 1 1 1, say, or if I give a matrix 1 1 1 1, can we immediately say that they are diagonalizable? Can I find a kind of linear transformation or kind of ordered basis with respect to which this becomes diagonalizable? So this is the motivation for studying this particular topic. So we'll try to find out what is the way out by which we can say that a particular linear operator is diagonalizable. And consequently, not only this, let me write, this rough work that I have done is just a rough work for you. My definition is not yet complete. Similarly, we can say that a square matrix capital A is called diagonalizable if LA is diagonalizable. And we know that LA is what? This is LA. LA has already been defined for you. So if we talk about the square matrix, then on the both sides, we have to consider we have to consider a matrix which is a kind square matrix. That means, as I considered over here, the matrix A to be a rectangular matrix belonging to M2 2 cross 3R. So if I talk about the square matrix, then we have to consider the matrix from M2 cross 2R or Mn cross Nr. Okay, so this is in general. LA is the matrix representation, which is defined in the following manner. This is the representation of LA. And its corresponding matrix capital A is diagonalizable if the linear transformation LA is diagonalizable. So the two things are actually similar. Now, remember that what I have written over here is just a definition. It is not a working criteria. So what is the working criteria? And how to find the diagonal matrix? The second question is actually very important. If such a basis exists, how to find such an ordered basis? Say, for example, if I consider my ordered basis beta to be consisting of the elements v1, v2, vn, which is a basis of v, such that T beta is a diagonal matrix. Then what we can say that for any of these vectors, we in general represent this vector by Vj. Vj can be any of these elements, v1, v2, vn, belonging to the basis beta. If I apply this transformation T on Vj, we will be able to write this particular transformation with the, we can express this particular transformation with the matrix representation, with the linear combination given by summation I goes from 1 to n dij vi. If I expand it, we will find that d11 v1 or d1j v1 plus d2j v2 plus djj vj plus plus dnj vj. And you know that all these particular elements will be off diagonal elements. And since I'm saying that my matrix is a diagonal matrix, so all these off diagonal parts should vanish, and we'll simply get djj vj, and we can rename djj, this matrix element djj, which appears in the jth row and jth column. We can call it as lambda j vj. Lambda j. We can define djj by lambda j, and this is just a notation. And it is happening because you have assumed that beta is a basis for which d beta is a diagonal matrix. Then this transformation will happen. Now, conversely, if we consider, say, beta is the ordered basis for B, is the ordered basis for V such that the transformation T of Vj is equal to lambda j Vj type of transformation exists for all scalars, lambda 1, lambda 2, lambda n. If such a transformation exists for all scalar quantities, then obviously this implies that the matrix representation of this linear operator will be of the form lambda 1 0 0 0 lambda 2 0 0 0 lambda n, which is obviously a diagonal matrix, and therefore this implies T is diagonalizable. Now you just look at the two parts of the two parts that I have discussed over here. Part one is one where I assumed, this is my assumption, this bit in both the parts, this part is common, that I have considered an
Can you
order.
explain this part once again?
Which part?
Sir, T of Vj. So where you explained using the summation.
Part one or part two? Summation part is that in both the parts, I have one particular thing is fixed, where I have written that beta, the set beta is the ordered basis for V. Here also I have assumed that set beta is an ordered basis for V. Here also I have assumed set beta is an ordered basis of V. What is the difference? In the part one, I already declared that T beta is a diagonal matrix. And I want to show you the transformation. Okay, and here I have not declared that T beta is a diagonal matrix. I started with the transformation and I want to show that T beta is a diagonal matrix. Now, if I consider T beta to be the diagonal matrix, so you think that each of the elements TVJ, that will each of the elements Vj of the basis, when T will operate on that, what will happen? They can be expressed in the following manner. Think about my previous problem that I was discussing. What was the problem? I took the basis element T1001 and that was expressed in the following manner.
Yes, sir, I understood that.
You understood? No, this is the point. And just a minute. I'm just writing one linear combination, you will understand. Now you see, when I'm talking about this particular element djjvj, actually I'm talking about these elements. This element is actually will be your d11. When you will get the next one, you will find something of this kind.
The elements of the column matrix.
Yeah. And
Okay,
this
sir.
will be d22 and so on. That will be d33 and that will be d44 when we express these in terms of the matrix representation. And when we'll find the matrix, all the other off diagonal elements will vanish. So therefore, this is all the ticked terms will vanish. All these tick terms will vanish from the picture. Only this will remain. So what is important in these two particular expressions is the following. One particular thing is coming out of this expression is the following result. We find that we have got such a kind of linear transformation, which is tvj equal to lambda j vj, which happens for all the basis elements. Okay, so we can say that for each vector v in the basis, beta, actually this relation is getting satisfied. TV is equal to lambda v type of relation is getting satisfied. When we talk about the identity matrix, IV equal to V, actually lambda is equal to 1 over here. Okay, so TB equal to lambda V. This type of relation is getting satisfied for the above, which is clear from our above discussion. And this happens for some scalar lambda. Okay, this is the basis of defining the eigenvalue and eigenvector. And consequently, the eigenvector and eigenvalues are defined in the following manner. So I'm going to give you the definition of eigenvector and eigenvalue right now. And in the next session, I'm going to talk about how to find eigenvalues and eigenvectors for a given matrix. So this is the basis of the eigenvalues and eigenvector. Okay, this particular representation is coming out of the above discussion. So now I'm going to define the terms, the new terms that have been introduced over here, that if T be a linear operator defined on a vector space V, a non-zero vector V belonging to V is called eigenvector or proper vector. We will not use these terms. We will only use eigenvector, the term eigen. Sometimes it is also known as latent vector. Sometimes it is also known as characteristic vector. Many different names are there. If there exists a scalar lambda such that TV is equal to lambda V, and the scalar lambda is known as eigenvalue or proper value or latent value or characteristic value corresponding to the eigenvector V, This much here. I'm actually stopping for the first session. In the next session, I'm going to discuss how to do the calculation to find out the eigenvalues and eigenvectors for a given linear transformation. So I'm stopping here right now. In the next session, I'm going to take the attendance.